All right, we have two chemicals here that are very close in structure. We've got acetone over here on the right, which is CH2O, and we've got methyl alcohol or methanol over here, which is CH4O, just the difference of a couple atoms. But we'll see that they are a little different in their properties. So if I shake these, they're both liquids at room temperature. But what we're going to do is see how quickly they evaporate. So the rate of evaporation of these liquids should tell us something about the intermolecular forces holding them together. So I've streaked them out onto the table. This is our acetone, and this is our methanol. And our acetone evaporates a lot quicker than the methanol. Even though they're both liquids at room temperature, okay, they can evaporate and free themselves into a gas if they're moving fast enough, and if they can free themselves from the intermolecular forces in between each other. So they both do evaporate fairly quickly, but one definitely does a lot faster than the other. So even though these molecules, acetone and methanol, are very similar to each other, we see a stronger attraction in the methanol and therefore a slower rate of evaporation. So these are both dipoles. We have a permanent polar kind of structure of the electron cloud here. We've got a dipole moment going this way. We've got a dipole going this way on this molecule. So why does this have such a stronger dipole-dipole force between molecules of this than this guy? So this is what's happening with our acetone. We have a dipole-dipole intermolecular force, since we have a permanent dipole on each acetone molecule. And they line up with the partially negative end by the oxygen going towards the partially positive end, like the hydrogen, of another acetone molecule. And this is the attraction between them. Okay? Now, if we look at the dipole-dipole interaction between two of these methanol molecules, it seems a little bit different. Okay? We have this oxygen-hydrogen bond, which has a greater electronegativity difference than, say, the carbon-oxygen bond that's right here. So we have a greater kind of dipole here that's got a stronger kind of difference in between the kind of the partially negative here and the partially positive here. So we end up with a stronger difference. We end up with a more polarized area of the molecule here than we would in the, say, this case. So that's one part of what makes this a little bit stronger. Another part is these can line up very nicely and kind of go opposite of each other. So we have kind of an attraction between the O and the H here and the O and the H here, okay, at the same time. We are limited to really having kind of like one interaction per a pair of molecules here, but here we have two interactions for a pair of molecules. So we end up with kind of more attraction going on in our methanol's case. Now, the most kind of important part of this that you'll see in other examples too is this electronegativity difference between the oxygen and the hydrogen. And it's what helps us define this specific dipole-dipole interaction as actually another kind of version that we give its own name. We call this hydrogen bonding, okay, because of the hydrogen that's involved that gives us the big electronegativity difference. That gives us something to kind of hang off of, that we have this very close in proximity, partially negative, partially positive, that can easily be lined up with another partially negative, partially positive zone on another molecule that has this kind of setup here. Now, oxygen is not the only thing that can do this with hydrogen to make this intermolecular force. And hydrogen bonding is not really a good name for it because it's not a bond, it's an intermolecular force. It's an attraction, not a bond. So it's not a perfect way of saying it, but it does show up a lot in chemistry and biology, and so it's a good thing to kind of keep in mind. So just to kind of recap, we can have a decent attraction between the partially negative and the partially positive ends of acetone molecules, but they pale in comparison to the way we can line up the partial negative, partial positive, partial negative, partial positive of two methanol molecules. We can get these very close to each other. Or we can flip them like this and give them even more room to do more attractions with other particles. So we get a stronger hold, and therefore they keep as a liquid better rather than just evaporating away as a gas. let's see if we can look at a couple more examples of hydrogen bonding, the special kind of dipole-dipole force. Let's look at some more examples that use hydrogen bonding. So what I've got here is ethanol or ethyl alcohol or denatured alcohol, all kind of the same product, and also ethylene glycol, right there, which are very similar chemicals, as you can see by kind of their SNATM models. Now ethylene glycol would actually probably be kind of rotated more like that. It's just kind of harder to see the markings I put on it when it's that way. Okay, so these two, again, are pretty similar. They're both liquids at room temperature. But before we test the evaporation rate, let me show you this. You kind of jiggle this around. It looks basically just like water for ethanol. Okay, nothing super exciting there. For ethylene glycol, let me see if I can get it to kind of shift back and forth. It's a little bit hard to see on the camera, but it's got a little bit more resistance to flow. It's not quite as liquid. It kind of, there you go. It's kind of almost like a gel, a little bit. It kind of takes a while to come back down. It's a little bit thicker. Okay, that is a property we call viscosity. It's a resistance to flow. Okay, and it's also another way we can see that something has stronger intermolecular forces than something else. Okay, now let's see if it also holds up for the evaporation rate. So let me take the cap off of this one. Let's see if I can do this one-handed. There we go. Right. I'll draw a line. The ethanol doesn't go away immediately, so it's better than acetone at least. Let's see our ethylene glycol. Okay, you'll be able to notice this kind of holds to itself better. It kind of bubbles up rather than this kind of lays flat. So this is what we call surface tension, where the molecules kind of hold together so well, you get a surface that kind of holds up against whatever it's laying across. It doesn't just splay out flat against the surface, against the table. We don't have as big of a bubble here if you kind of check down flat with this compared to what we have here. Water has some very good surface tension as well, and it has to do with hydrogen bonding. Okay, these are both holding up pretty decently as far as evaporation goes, but based on the viscosity, oh, this one's starting to evaporate. Okay, based on the viscosity and the surface tension, okay, we are seeing that our ethylene glycol has some stronger intermolecular forces, which is a little interesting. That one continues to evaporate. This one's still holding together pretty well. Now, surface tension kind of has to do with the competition of two different kind of perspectives on attraction and intermolecular forces. Okay? The intermolecular forces between molecules of the same substance are what we call cohesive forces because they cohere to each other, they cooperate with each other. Okay? And the intermolecular forces between a substance and the surface that it's on, or the container that it's in, is what we call adhesive forces. So in the case of our ethylene glycol here, we have stronger cohesive forces that hold these molecules together rather than the adhesive forces that hold this to the table. In the case of the ethanol, it's a little bit more of an even battle, which is why we don't have kind of as much bubbling up over the surface. The cohesive forces are just about as strong as what's holding them to the table and allows them to kind of lay out here. Now our ethylene glycol has not really budged yet. It's still a pretty viscous liquid there. Our ethanol is pretty much gone. And then just kind of compare. It looks like maybe a little bit is evaporated in this center line here, but otherwise not super exciting. Okay, so why is this? Well, our ethanol holds up pretty decently because its dipole-dipole interaction is a special kind of dipole-dipole we call the hydrogen bond. Okay, it has hydrogen bonding because of this big electronegativity difference, and therefore a strong dipole moment, a strong dipole between the oxygen and the hydrogen that are very close together and kind of work well with other hydrogen kind of bondable, is a bad way to put it, but other stuff that can do this sort of interaction. Okay, ethylene glycol has the same thing, but twice. It's got two of these. Okay, so should be twice as much hydrogen bonding, twice as many of those special dipole-dipole interactions, and therefore should be about twice as strong. Let's do one more comparison with this special dipole-dipole attraction we call hydrogen bonding, which again is not really a type of bonding, it's just another intermolecular force, and it's badly named. In this case, we have rubbing alcohol, aka isopropyl alcohol, also known as isopropanol, okay, along with glycerin, or also called glycerol, which is right here. So just looking at the two structures, they're very similar, okay, kind of same number of carbon atoms, okay, but one of them has more of these little OH groups, which are fantastic for hydrogen bonding because of the great electronegativity difference between the oxygen and the hydrogen. This makes a great strong dipole with a very kind of differentiated partially negative and partially positive here. It's a great splitting of the charge, and therefore makes for great intermolecular forces between molecules of the same stuff. Okay, so let's test these guys out. So this is my isopropanol. Streak some of that out on the table. Get some of my glycerol here. Ooh, and you can already kind of see this is like very oily. So like the ethylene glycol, you can expect this to be pretty viscous due to its strong intermolecular forces. I'm going to put the cap back on this so that way I can really shake it. You can also see, like the ethanol, this is laying pretty flat, whereas this really bubbles up. Okay, there's a strong intermolecular force that causes a lot of surface tension here. Okay, some of our rubbing alcohol has started to evaporate. Okay, it's going pretty fast. All right, again, very little surface tension, not as strong of a cohesive intermolecular force in between these molecules compared to what's going on here. Okay, so again, our rubbing alcohol molecules are escaping from the liquid phase into the gas. Okay, while our glycerol is still just kind of sitting there. Okay, just to kind of cut to the chase, this glycerol is not going anywhere. I can leave this here for days and days and it will not evaporate. I have to clean it up with soap and water. Okay, let me shake this so you can see just how viscous this is. Okay, again, there's a great resistance to flow. As like I move this and then it kind of has to catch up with me and start flowing again. If I tip this over, it has to like run down the side. It's almost like syrup. Okay, so that's a good indication of strong intermolecular forces, again, cohesively between the molecules of glycerol. Okay, this is all thanks to all of these OH groups that can hydrogen bond with each other. So with each pair of molecules that gets close to each other, you have a lot of hydrogen bonding that can happen in between these. And like the ethylene glycol, these might not be all, you know, on this top here. We might be able to kind of rotate this group so it's kind of down like that. And rotate this group so it's down like that. It's just a little bit easier to point out when I've got them all facing the right direction, the same direction. Okay, compared to this guy over here that's only got one of these, where we've got a really good kind of dipole on this end of the molecule here, a really good kind of difference between our partially negative and partially positive charges. In comparison, whenever we have something like this with an oxygen atom or some other electronegative thing like fluorine or chlorine or bromine, nitrogen, the rest of the hydrocarbon, like this stuff here, carbons and hydrogens, don't really do much. We kind of end up ignoring them because they're going to be nonpolar in comparison. Even if there's a little bit of a polarity difference, these are kind of the dominant places we're going to have intermolecular forces take place. Oxygen, nitrogen, and fluorine are really the only three elements that can make a big enough electronegativity difference with hydrogen to participate in hydrogen bonding. Now, as a result, you can still have something like an OH, an NH, or an HF go and donate a hydrogen bond attraction to just another dipole, and that could still count as hydrogen bonding. But you've got to at least have one hydrogen atom that is bonded to something like oxygen, nitrogen, or fluorine that's very electronegative to get hydrogen bonding to happen, to get a dipole-dipole interaction to specifically be classified as hydrogen bonding. So in this case, we've got our oxygen and our hydrogen bonded together, and the dipole-dipole interaction in orange there is our hydrogen bonding intermolecular force, shown here with our SNATOS models. In our NH3, we've got this nitrogen-hydrogen bond here that has a big electronegativity difference. We got a strong dipole, and so that attracts to another dipole on another NH3 molecule, shown also here. This also is a good example of how three-dimensional shape is very important for how these come close to each other and how they can attract to each other. We can't just say, there's three partially positive hydrogens here, and so they all, attract to this negative charge here. They don't spatially line up like that. But they might spatially line up with other NH3 molecules around it. And then we've got our HF, which is pretty self-explanatory there.